So let's try our next one. So now we don't want to just have one machine. We want to have multiple machines. So let's say I want to schedule n jobs on m parallel machines. So in this graph, we can see m is 3, n is 8. We are scheduling 8 jobs to 3 machines. So again, we have the index set for a job. So jobs, we have job 1, job 2, up to job n, and they have processing time. We call each PJ. So a job can be processed by any machine, but it can be processed on only one machine, okay? So if you schedule job 1 on machine 1, then there's no way for job 2, for machine 2 and the machine 3 to help in processing job 1, okay? Job 1 belongs to machine 1. So now the thing is that, again, different schedules gives this machine different completion time. And now what we want to do is to minimize Makespan. So there are two definitions for Makespan. Either you count the completion time for all the jobs and find the one that has the latest completion time. Okay, so that's one thing. Another thing is that for each machine, you count the completion time and find the last one. So basically, it's the same. The latest completion time for job or latest completion time for machine, pretty much that's the same. So that's our target. We want to minimize Makespan, or we want to balance the loading for all the machines. All right. We want to make sure that all the machines pretty much are doing a similar amount of work. So now let's try to formulate this problem. We want to minimize Makespan. So as long as some jobs are assigned to a machine, now we know the sequence on that machine does not matter, because we only care about when is the last job finished. And then there's no reason not to start your next job once you complete this job. So pretty much we may understand on each machine I, given the assignment, how may we calculate its final total processing time. So let's see this. When we want to minimize Makespan, pretty much all we need to do is to do job assignment. We don't need to do job sequencing. On each machine, we don't care about the sequence. I hope that makes sense. So to do assignment for job J and the machine I, let's say Xij is 1 if job J is assigned to machine I. So somehow that makes sense. And then for machine I, the last job would be completed at this particular time moment. So these labels which job is assigned to myself. And then for each job, if it is assigned to me, then I collect its processing time. And then the sum of all these processing times is the completion time for myself. Okay? So that's one thing. This is pretty much an expression for machine I. For machine I, this is the completion time for machine I. Okay, so now we know we have the definition for Makespan. Makespan, let's call it W. Makespan is the maximum completion time among all machines, right? So if you have several machines, their completion times 50, 90, 60, 80, and so on. And you say you have a value called W, which is your Makespan. Then very naturally, you do have this constraint. For each I, for each machine I, we know the Makespan is not going to be smaller than the machine completion time, because that violates the definition for Makespan. So now let's collect everything. We want to minimize our Makespan. And we know for Makespan, it satisfies this condition. The Makespan is greater than or equal to the machine completion time for each machine. And also for each job, it must be assigned to at least it must be assigned to exactly one machine. And finally, these things are binary. So we are pretty much done with this formulation. The only question that remains is that how may we ensure that W is indeed the Makespan? So why do I ask this question? Consider this example. So suppose I have three different completion time, right? So the completion times are here, which may be calculated by taking a look at Pj and Xij. So if they have these machine completion times, this particular constraint is saying that your W cannot be here. Your W cannot be here, cannot be here. Why? Because if your W is here, for example, then it does not satisfy this constraint for the second machine. Alright? So your Makespan must satisfy this constraint. But is the other way true? When you have a value satisfying all these constraints, is it guaranteed to be a Makespan? Well, probably you would say is no, because if all these machines finished at 60, 80, and 90, we actually may set W to be 100. It still satisfies all these constraints, right? So maybe you would be confused about why we say this is a complete formulation. The answer is here. Because you are minimizing your W. So if you say W is 100, in this case, there's no way for your W to be 100 actually, because the minimization objective function is going to cut down W as much as possible until W equals to the maximum of these machine completion times. Okay? So with this clever design, we may use this part to specify the Makespan. And the minimization problem naturally helps us to formulate this problem by considering the objective function and the constraints at the same time. So this is about Makespan minimization on parallel machines.